All right, hi, and welcome to our first class. I'll turn on the pen tool here and we'll begin to take notes. So, our first topic is energy, power, and efficiency. Energy is the ability to make something happen, and we'll be concerned with, in this course, several different types of energy. The chemical energy, for instance, the energy stored in the bonds of food or in the chemical bonds of gasoline. Kinetic energy is the energy of a moving object, and when we need to, we will calculate it as follows. Kinetic energy is 1/2 mass times velocity squared. This is an SI unit, so the mass will be in kilograms, the velocity will be in meters per second. Potential energy is height energy, and the potential energy, say, for water behind a dam, is the mass times the Earth's gravitational field times the height above a reference surface. So the mass is in kilograms. The gravitational field strength of the Earth is 9.8 newtons for every kilogram, and h, the height above the ground, would be measured in meters. Thermal energy is the energy of a hot object, and that we'll calculate later. Okay, now the units of energy, well, you see a number of different versions up here, but each of these is equivalent to a joule. If you multiply mass times velocity squared, you'll get kilograms times meters squared per second squared, and that is what a joule is. So here we can say 1 joule is defined as 1 kilogram meters squared per second squared, or we can also write this as 1 kilogram meters squared seconds to the negative 2 power, okay, because a negative exponent is the same as a reciprocal. So that is the dimensional definition of a joule, okay? Now, in addition to these base units, we will also use a lot of metric prefixes. So these we'll probably give you a list, but you should probably learn to commit them to memory. For instance, thousands is kilo, mega is millions, 10 to the 6, giga is billions, 10 to the 9, and then the higher ones, tera is trillions, peta is 1,000 trillion, and an exajoule is a billion billion, is 10 to the power of 18. Okay, other units for energy include the British thermal unit. 1 BTU is just a little bit more than 1,000 joules. It's 1,055 joules. And then there's a calorie. This is often used with, say, food. And 1 calorie, capital C calorie, is 4,186 joules. Now, these conversion factors will generally be given to you, but it's helpful if you can remember them. Okay, so here's an exercise in unit conversion. A barrel of oil, that is equivalent to 5.6 million BTUs of chemical energy. We just want to take that number and convert it to joules. So we have 5.6 million. Now a million is 10 to the 6, or 6 zeros. So we've got 5.6 million British thermal units, or BTUs, of energy. We want to convert that to joules. We'll do that using a ratio technique. So we'll put the BTU unit down here to cancel, and then we'll put the joule unit up here to replace. And now we just put in numbers here so that the top and bottom are the same, so that essentially we're just multiplying by 1. Well, we see from above that 1 British thermal unit is 1,055 joules. So when we multiply this, we see that the BTU units will cancel out and we'll be left with joule units. Okay, so we just paused to multiply those together, and you see the result up over here. It's 5908000. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9 powers of 10. So that is going to be 5.908. Let me do this again. 5.908 times 10 to the 9 joules. I can just here divide by 1e to confirm. Yeah, it's 5.908 times 10 to the 9 joules. Looking back on the previous page, we see that 10 to the 9 is a giga. That's a giga. And I see I was getting ahead of myself here. This of course, is not, should be a joule, right? And not a giga, because it's 5.908 times 10 to the 9 joules. So the 10 to the 9 is a gigajoule. So we can write this as 5.9, well, it's about 5.91 gigajoules. Okay, so there is our very first unit conversion, and unit conversions is something we'll do quite a bit of in this course. So we're actually just going to practice some of them here today. All right, so let's continue then. Another important quantity in our study will be power. And power is defined as the ratio of energy per time, or work per time, as we'll see later. So power equals energy divided by time. And so in terms of the units, we have joules over seconds. So power is in joules per second, or joules seconds to the -1. And this is defined as a watt, named after James Watt. So that's our definition of power. And again, we'll use a lot of metric prefixes. So a kilowatt is 1,000 joules per second, or 1,000 watts. A megawatt is 1,000,000 joules per second, or 1,000,000 watts. And a gigawatt, gig is 10 to the 9, so this is 10 to the 9 power joules per second. There are other units of power, so horsepower, this is the imperial unit of power. This is equivalent to 746 watts. And this is a unit that's used quite a bit, a BTU per hour, and that's just a conversion exercise to convert that to watts. Because a BTU is 1,055 joules, and an hour is 3,600 seconds. Okay, well, I said I'd leave it as an exercise, but here it is. So you can see this is going to be about 1/3 of a watt, because you just do the division here. So let me pause this again. Okay, so calculation shows this is equivalent to 0.293 joules every second, or 0.293 watts. All right, so here's another unit that comes up a lot, a kilowatt hour. Kilowatt hour. Is that an energy unit or a power unit? Well, you see kilo, which means 10 to the 3. Then you see watt, so kilowatt, that's 1,000 watts. So at first glance, it looks like a power, but then you have hour there. So you're really multiplying a power by a time. So, and a power by a time is actually an energy unit. So kilowatt hour is an amount of energy that you've used. Let's expand that a little bit and we'll see that. So kilowatt hour, kilowatt is 1,000 watts. And there's implied multiplication here. So you're multiplying kilowatt, 1,000 watts, by hour. Now to expand that further, we could say that's 1,000 watts times 3,600 seconds. And then of course a watt, as power, is a ratio of energy over time. A watt is a joule per second. So now from the units, it's clear that we're multiplying joules per second times seconds. Seconds cancels. What survives is joules. So kilowatts times hours is a unit of energy. It's joules. And if you work it out here, you're going to get 3.6 million joules. So that's 3.6 times 10 to the 6 joules. And again, I prefer the metric prefixes because it's faster to write and easier to type than scientific notation. So a kilowatt hour is 3.6 megajoules. We are going to use that a lot in our course. So this is an equivalence that we'll make a lot of use of. For instance, if you had used 2,000 kilowatt hours of electricity that month on your bill, how many joules did you just use? Well, this is again really just a unit conversion. So there's the amount of energy we use, 2,000 kilowatt hours. And we want to change that to joules. So we'll use the equivalence between joules and kilowatt hours. Well, we just showed here that 1 kilowatt hour was 3.6 million joules, megajoules. So this and this are equivalent. We're really just multiplying by 1 here. When I do this multiplication, though, kilowatt hours cancels out, and I end up calculating the number of megajoules that I've used. So 3.6 times 2,000 is 7,200 million joules. So now we're going to do a little scientific notation trick. There's another 3 powers of 10 here, right? This is 7.2 times 10 to the 3. And remember that mega is 10 to the 6. That's 6 powers of 10. So I've really got 3 powers of 10 and 6 powers of 10. I've got a total of 9 powers of 10 here. So 1,000 mega is really a giga. It's 10 to the 9. So my 2,000 kilowatt hours of electricity that I use is equivalent to 7.2 gigajoules. Okay, here's another problem for us. Light bulbs are often rated in watts. That just means that, say, a 120-watt light bulb is using 120 joules every second. Let's imagine that you leave that light on for 3 hours at night every single night of the year. How much energy do you use in the year? Well, we're using, we know that energy, oh, that's horrible handwriting. Energy is the ratio of power over time. Oh, I know why it's horrible, because I'm writing with the wrong end. There we go. So, and that's all totally wrong. I'm really off to a terrible start here. Power is the ratio of energy to time. Now we're off and running. So that means if I want the energy used, I'm just going to take the power multiplied by the time, because rearranging this formula, power multiplied by time will equal energy. In physics symbols, an energy is a power times a time. And that's not surprising, because we just showed that kilowatts times hours was an energy. Our power in this case is 120 watts. And our time is, well, there's lots of time here because it's 3 hours every day. And then there's 365 days in a year. So this will be the amount of energy that we use per year. 3 hours every day times 365 days. So the days cancel out. Multiplying this will give me the hours, and then I'll end up with the number of watt hours. Now, of course, I could make this joules per second, and I could make this seconds. So we got 120 watts, 3 hours times 365. The days is already canceled. And then there would be 3,600 seconds in every hour. So that would now give me watt seconds. But of course, a watt, that's a joule per second. So let me wipe that out and replace it with a joule per second. So now the seconds cancel out, and I find the number of joules of energy that I use in a year of using this light bulb, leaving it on 3 hours every single day. Okay, so calculations show this works out to be 4.73 times 10 to the power of 8. So that's 473 million joules. 473 times 10 to the 6 joules, or 473 megajoules. So I'm moving 2 powers of 10 from the 8 over here to make it 473. That's why the power dropped from 10 to the 8 down to 10 to the 6. And that's how I went from 4.73 up to 473. So that's the amount of energy used in a year. That's in joule units. Now, in terms of working out the cost, it's convenient to use other units because electricity in BC is priced in cents per kilowatt hour. So let's go back to our calculation right here, this line right here. And for our cost, it's going to be equal to the amount of energy times the unit cost. Okay, so how much energy do we use? Well, we know it was 120 watts. Now again, I could put in this megajoule amount, but it's convenient to go back here. And then I've got 365 times 3 hours. So let's just work out what that is. 3 times 365, there it's, what is that? That's 1,095 hours. Now, this 120 watts is actually 0.12 kilowatts, because kilo is 1,000. So what I'm showing you is that if you work out your energy as a power times time, and you express the power in kilowatts and the time in hours, when you multiply those together, you naturally get kilowatt hours. So we see that we've got 0.12 times 1,095, so let's just see how much that is. Times 0.12, we've got 131.4 kilowatt hours. So that's our energy. We, of course, need to multiply this by this cost still, right? Which was 7 cents for every kilowatt hour. Now that's not really useful till we get down to this very last line here, because now with our energy in kilowatt hours, the kilowatt hour part just cancels out. So there was our energy, 131.4 kilowatt hours. Cross that out with this, and we see we get an answer here in cents. So how many cents is that? So it's 131.4 times 7. That's 919 cents. 919.8 cents, or in dollars, that's $9 and about 20 cents to use that light for the entire year. Okay? And that's a pretty high wattage bulb. That might be like a security light that you'd have outside in your yard. So the annual cost is $9.20. Really, that's not a very large cost. Electricity is a tremendous bargain. You're getting almost 500 million joules for less than $10. Where do you get something, that price with that amount of money these days? So one of the results of the textbook, an important result, is that for every household, 2.5 person household on average in Canada, about 600 billion joules, 600 gigajoules is used. And that breaks down as follows, and this is all the activities that we're involved in. We use about 105 of those gigajoules in our homes, some for heating the house, some for heating the water. This is for our appliances, our fridge, etc. There's about 4 gigajoules for lighting and about 2 gigajoules for cooling purposes. So that's our residential use. This is industrial use. This is the energy used to, mine and refine metals, for pulp and paper industry, for all the high-tech industries, everything in Canada. And each household is responsible for a portion of that. This is transportation. About half of that is just energy used in our cars. The other bit is for freight and for airlines and for trains to bring us to our vacation destinations and to bring us all the things that we like to eat and buy. 117 gigajoules per year, that is commercial and industrial. So this runs the office buildings, the schools, the hospitals, the shopping malls. 17 gigajoules per year, that's the energy use in agriculture. So this is the diesel fuel to run the tractors. It's the electricity to run the pumps in the barns and the lights in the barns, all of those things. So this is our energy budget per year per household. Now, we make a distinction between direct and indirect energy. Some energy is direct, where you use the gas and you burn it. You use the natural gas and you furnace. You use the electricity to run your lights. So you actually use that energy. Indirect energy is the energy that's used to make things. So if you buy a phone, then there was a tremendous amount of energy that was used to make the silicon, to make the logic chips that are in that phone and make it work, to make the glass, to make the plastic case, etc., etc. So that's indirect or hidden, or we'll use the word later on, embedded in the stuff that you buy. Now, a helpful visual tool, we're going to show that the 32 watt bulb on all the time is equivalent to a gigajoule per year. So a 32 watts on all the time, that would be 32 watts is 32 joules every second. And if we leave it on all the time for the whole year, well, that would be 365 days in a year, and there's 24 hours in a day, and there's 3,600 seconds in an hour. So multiplying this all out, we get the number of joules per year. Okay, so let's see how many joules per year 32 watts is. So there's 32 joules every second, 365 days in the year, 24 hours in the day, 3,600 seconds in an hour. We see it's 1.009. Let me go back here and I'll just divide by 1, E9. And you see it is 1.009 times 10 to the 9, or gigajoules. So a 32 watt light bulb, if you leave it on all the time in a year, uses a gigajoule. So up above, we said that our lifestyle was 600 gigajoules. That's the amount of energy we use in all our activities in our households. So we can think of our lifestyle as being equivalent to 600 light bulbs on all the time for the whole year. Okay, that's the amount of energy we use. Now, for our lighting purposes, we're using about a little bit more than 4 gigajoules, about 4.3. So all our use of energy for all our lighting purposes at home works out to about 4 32 watt light bulbs on all the time. And what we want to study today is, well, we want to learn about our use of energy. We want to learn about the energy, about the units and how to do conversions. And we also want to study our use of lighting energy and try and analyze how it is that we use this much. Okay, another really important concept for us here is the concept of efficiency. Now, efficiency is represented by a Greek letter eta. It's kind of like an N with a long monkey tail on it. And efficiency is the ratio of output, how much useful output you get, and that could be the useful energy or the useful power, per unit input. So you're going to take the amount of energy or power output and divide by the input. And this is always going to be less than 100%, less than 1 or less than 100%. Now, the reason for that is that the input energy, some of it is converted to output, but then there's always a little bit of thermal energy, Q, that's created in the process. And this is typically thought of as waste heat. So when you burn gasoline, some of it makes the car go, and the rest just heats up the air in the road. Okay? So this is the concept of efficiency. And we could just highlight this here. In most processes, the remainder is converted to thermal energy. That's what this second relationship says right here. So for instance, you climb the stairs and use 600 joules of food energy. Your muscles are 20% efficient. How much potential energy do you gain, and how much thermal energy is produced? So we have to decide whether we're dealing with an output or an input. Okay, now in this process, you are burning food energy, so that's what you start with, and you end up with potential energy and thermal energy. So our efficiency in this case is the ratio of the energy output and the output is going to be the potential energy, over the energy input. The input to this process is the food energy. So in this problem, we're given the food energy as 600 joules, and we're given the efficiency. We're asked for the potential energy. We see that to solve for potential energy, we're just going to multiply efficiency by food energy. So just rearranging that formula, it'll be the efficiency multiplied by the food energy. So this 600 joules of food energy that you burned, because your muscles are 20% or 0.20 efficient, only 20% of that 600 joules ends up being converted to something useful, which is the height energy. So you're going to end up with 120 joules of height energy. What happens to the rest of that 600 joules of food energy? Well, the other 80% gets converted to thermal energy. That's our conservation of energy equation right here. The energy input equals the energy output plus the thermal energy. Rearranging that, the thermal energy is the input food energy minus the output potential energy. So it's the 600 joules of food energy that you burned in your muscles minus the 120 joules of height energy that your body gained. You are going to produce 480 joules of thermal energy, and that thermal energy will get transferred from your muscles via your blood to your skin, and you'll have to get rid of that to the environment, or your body will overheat. So this concludes our first lesson, and you can play this back and listen to these examples as many times as you like, and they should guide you and enable you to do the assignment for this first week of class.